Welcome to the Deep Dive. I'm your host, and today we are getting into some seriously fascinating stuff.
Yeah, we really are. It's great to be here.
So we always take a stack of, dense sources, articles, research papers, training manuals, and we just extract the insights you actually need to know. And today we're tearing apart the official training materials for the world's most massive cargo ships.
The really, really big ones, the absolute leviathans of the ocean.
Exactly. And usually, right, when we think of a colossal freighter just moving across the ocean, we picture it as, just a sealed steel box.
Right. Just cold, hard engineering.
Yeah, exactly. You build a huge metal container, you stuff it full of goods, lock it tight, and just send it across the Pacific.
Which, makes sense. The assumption there is that total isolation from the outside world is the ultimate goal. I mean, you want to keep the ocean out, so you seal the box.
That's what I would assume.
But when you actually dive into the engineering schematics and the operational manuals for these maritime giants, which we have right here in front of us, that assumption just completely falls apart.
It really does. Because what these training materials reveal is that a modern cargo ship isn't a sealed box at all. It actually behaves a lot more like a massive living organism.
Yeah, that's a great way to put it.
And today, for this deep dive, you aren't just a listener sitting at home or, commuting to work. Today, you are stepping into the heavy boots of a maritime trainee.
Welcome aboard.
Seriously, welcome aboard.
Uh-huh.
Our entire mission today is to basically explain the working mechanisms of the cargo hold ventilation system in a simple way for trainees.
Good.
And the bilge system, too.
Yeah.
We're demystifying how these colossal ships stay alive.
Because to keep millions of dollars worth of cargo safe, the ship has to constantly interact with its hostile environment. It's not passive.
Right, it needs lungs to breathe, which is its complex ventilation system, and it needs kidneys to process and expel unwanted liquids, which is its bilge system.
Taking on that trainee mindset is really the perfect way to approach this material. Because we aren't just looking at theoretical physics today, right? We are looking at literal survival mechanics.
Yeah, survival mechanics for billion-dollar assets.
Exactly. We have this fascinating stack of schematics, real-world photos, operational protocols right in front of us. And you really need to understand how the ship manages the relentless flow of air and water, because if these systems fail,
The cargo is toast.
the cargo is completely lost, and potentially the ship goes down with it.
Okay, so let's start with the respiratory system, the lungs of the ship.
Perfect.
Before we get into the physical hardware, like the heavy metal pipes and the giant deck vents we see in these photos, we need to understand the two, fundamental philosophies of how air is moved through a giant cargo hold.
Right. According to the manual, a ship breathes in one of two ways. You have natural ventilation or mechanical ventilation.
Okay, so let's unpack this. Mechanical ventilation is also, what do they call it here? Forced ventilation.
Right. Yes, forced ventilation. You'll see both terms used interchangeably in the manuals.
Got it. But as a trainee, understanding the natural method first is absolutely essential, right? Because it relies on just the physical properties of the environment.
Mm.
You aren't throwing an electrical switch.
Right. No motors, no power.
To put this in everyday terms for you, I like to think of natural ventilation as simply, opening the windows on opposite sides of a stuffy house. You just get a cross breeze going.
Exactly. You're letting nature do the heavy lifting for you.
Yeah. And then mechanical ventilation, on the other hand, is like flipping on a heavy-duty exhaust fan in a windowless bathroom when things get way too humid. You're actively powering that airflow.
That's a really solid analogy.
But I'm looking at the text here for the natural ventilation system, and there are absolutely no electrical fans or motors mentioned anywhere in the schematic. So how does a giant steel box the size of a skyscraper just, naturally breathe on its own?
Well, it comes down to one fundamental force of physics, which is convection.
Convection, okay.
Yeah, natural ventilation relies almost entirely on air circulation driven by convection currents.
Wait, so just pure thermodynamics, like literally just hot air rising.
That is the core engine of it, yes. Consider what is actually sitting inside these massive cargo holds.
It's a lot of stuff.
Right, and it is rarely just inert plastic. You might be carrying tens of thousands of tons of grain or coal or, organic materials.
Oh, wow.
And grain, for instance, actually sweats.
Wait, grain sweats?
Yeah, it releases moisture and heat as it sits there. Coal can off-gas methane and heat up significantly on its own, Furthermore, you have this massive steel hull baking in the sun as it crosses the equator.
Oh, man. So the inside of the hold essentially just becomes an oven.
It becomes a highly pressurized, thermally active environment. So the hot air inside the hold naturally wants to rise.
Because hot air expands and goes up.
Exactly. As it rises and escapes through vents located high up on the deck, it actually creates a slight vacuum, a pressure differential deep down in the hold.
Okay, I'm tracking.
And this vacuum pulls the cooler, denser sea air in from the outside. Add in the forward momentum of the ship physically pushing through the atmosphere, and you have a massive, continuous exchange of air.
Outside air enters, inside air exits, completely passively.
Yes, no electricity required.
That is brilliantly simple. You're basically turning the entire ship into a passive vacuum cleaner.
It's elegant engineering.
But okay, here is where my trainee brain gets totally hung up. Since natural ventilation relies on this free flow of air, how is the ship actually built to capture it without, well, sinking? Because we're talking about the open ocean. You can't just leave giant gaping holes in the main deck to let the air out. The first massive wave that crashes over the bow is going to pour straight down into the cargo.
And that right there is the fundamental engineering tension of ship design. Every piece of metal on the deck serves a dual purpose.
How so?
It must relentlessly facilitate that convection current we just talked about, while simultaneously fiercely protecting the delicate cargo from the absolute violence of the ocean.
Wow. Okay, let's bring this to life by looking at the actual structural design. I have a photo from the training deck right here. So picture this. You're standing on the main deck of a colossal cargo ship.
And the scale is just massive.
Oh, it's huge. The steel under your boots is painted this bright industrial red. And protruding up from the deck, spaced out along the edges, are these large, black, louvered vents.
They look a bit like grills on a car, almost.
Yeah, honestly, they look like heavy-duty air conditioning grills. And hinged right above them are these thick, bright yellow steel flap covers, and they're propped wide open to catch the sea breeze.
And the companion photo in the manual shows you the reverse angle, which is really cool.
Oh, right, the one from inside.
Yeah, if you were standing down inside the cavernous cargo hold, looking straight up at the ceiling, you would see rectangular openings set deep into the heavy structural support beams.
That's where the outside air is pouring in.
Exactly, right through the ceiling of the hold.
So structurally, how do these two ends connect? Because I'm looking at the schematic for this natural ventilator, and the labels describe a very specific pathway.
Walk me through what you see.
Okay, so at the very top, there's a lifting eye, which just looks like a heavy metal loop.
Yep.
Below that, the main body of the vent is labeled the ventilator coaming. And then, extending straight down through the deck, is something called the trunking. Is this trunking basically just a giant metal windpipe routing the air down into the belly of the ship?
The trunking is the literal airway, yes. It channels that convection current deep into the lower reaches of the hold, ensuring the fresh air doesn't just skim the ceiling, but actually circulates through the cargo.
Okay, that makes sense.
But the true genius of the structural design and the answer to your earlier question about keeping the ocean out lies in that ventilator coaming.
The coaming. That's the section sitting raised above the deck level, right?
Yes. A coaming in maritime architecture is essentially a raised, heavily reinforced border or collar surrounding an opening. You have to picture the reality of the North Atlantic in winter. You have green, water-solid, heavy waves washing violently over the deck of the ship.
Just tons of freezing water smashing into everything.
Exactly. The coaming elevates the air intake safely above that wash. It acts as a fortress wall. When sea spray or heavy rain hits the deck, the water hits the wall of the coaming and flows around it.
Oh, rather than simply pouring straight down that giant metal windpipe into the cargo.
Precisely.
So it's a protective collar that lets the ship breathe without drowning.
That is so cool. And I'm assuming that lifting eye at the very top is just a practical addition, right? Like cranes probably need to hook onto that metal loop to remove or service the massive head of the ventilator when it gets damaged.
You got it. Maintenance on a vessel of this size requires heavy machinery. You cannot simply unscrew a steel vent cap by hand. The lifting eye is a mandatory design feature for shipyard repairs.
Okay, so that covers the natural breath of the ship. It's a really elegant system.
It is when it works, right? But nature is notoriously fickle. What happens when convection just isn't cutting it? Let's say the ship hits the doldrums and there's absolutely zero wind. Or worse, what if you're carrying a type of hazardous cargo that demands strictly controlled, massive airflow to prevent explosive gases from building up?
Right, regardless of the temperature outside.
Yeah. Relying on a gentle cross breeze isn't going to save you that.
It certainly isn't. When nature fails to provide the necessary pressure differential, or when the cargo dictates a specific number of air changes per hour, the ship must abandon the passive approach. You have to force the issue.
And that brings us to the mechanical or forced ventilation system.
Exactly. The hardware changes significantly when we look at this second schematic.
It really does. The manual describes mechanical ventilation as a system where the movement of air is driven by massive electrical fans mounted directly inside the ventilator shafts.
And the visual evidence provided in the training materials for this is quite intimidating.
Oh, it really is. The photo looking up from inside the hold shows something entirely different from the natural vents. Mounted directly into a square housing in the ceiling are these massive, heavy-duty metal fan blades. It looks less like a vent and more like an industrial wind tunnel.
It's serious machinery. And to understand how that wind tunnel operates safely, we have to examine the schematic of the above-deck components. The forced air system introduces entirely new mechanical elements.
Okay, let's break those down. At the very top, instead of a hinged flap cover like before, we have a wide, flat, umbrella-like cover labeled the mushroom cap.
Yep.
Below that, housed securely inside the vertical pipe, is the blower, which is the electrical fan motor. And below the blower, sitting inside the protective coaming, is a critical label that says fire flap.
The transition from natural to mechanical ventilation introduces a severe new risk profile to the ship, and those specific components are the answer to that risk.
This is where it gets really intense for me, because if I put my trainee hat back on and think about this logical...
Let's hear it.
Well, fire needs oxygen to survive, right?
Absolutely.
If you have a massive industrial electrical blower actively forcing highly oxygenated air deep into a cargo hold and a spark ignites down there, wouldn't that blower just act like a giant blacksmith's bellows feeding a furnace? You'd be pumping premium fuel straight into a fire.
That is the exact kind of critical deduction a maritime trainee needs to make. Introducing forced air fundamentally alters the survivability of a disaster at sea.
Because you've turned a slow burn into a blast furnace.
Exactly. A cargo fire is arguably the most terrifying event a crew can face. I mean, you are thousands of miles from a fire department, floating on an ocean with tens of thousands of tons of fuel underneath you.
Because you've taken away nature's slow pace and substituted it with industrial power, you are force-feeding the environment.
Right. So the system requires absolute fail-safes. The mushroom cap at the top performs the everyday defensive work. Its aerodynamic shape acts as a shield, deflecting heavy sea spray and weather away from the sensitive electrical blower motor.
While still allowing the forced air to escape from underneath its wide brim.
Exactly. But the fire flap is the life or death mechanism. It is housed securely inside the thick metal casing of the coaming.
Go.
If a smoke detector triggers in that hold, the absolute first priority before water is even considered is starving that environment of oxygen.
Like a suffocate the beast.
The blower motor must be immediately cut off, and that fire flap must be slammed completely shut to seal the airway. It physically chokes off the ship's windpipe.
Man, it's incredible to think that the difference between containing a fire and losing a billion-dollar vessel comes down to a heavy flap of metal slamming shut in a vent.
It really does. It's a vital safety mechanism built right into the lung of the ship.
It isolates the hazard.
Yes. If you seal the hold effectively, the fire will eventually consume all the available oxygen and smolder itself out.
Okay, so we've successfully mapped the air flowing at the very top of the cargo hold. We completely understand the respiratory system.
The lungs are covered.
Right. But gravity dictates that while air rises, anything heavy is going to sink to the absolute bottom. And in a marine environment, the most persistent, insidious threat isn't just fire, it's water.
Which brings us from the ship's lungs to its kidneys.
Yes, we're transitioning to the cargo space bilge systems, the filtration and expulsion mechanisms.
The manual states the purpose of the cargo space bilge system with brutal simplicity, actually. Its job is to remove water from a cargo space.
And it is crucial to note the emphasis on water there, right?
Very crucial. The cargo bilges are designed to handle seawater, rainwater, or condensation. They're not designed to process massive oil spills or hazardous chemical leaks from the engine room.
Right, that's a completely different system.
Exactly.
So structurally, the schematics show us that to catch this water, the holds have these recessed areas called bilge wells, and they are located at the very bottom on each side.
Yeah.
Specifically, tucked away in the deepest recesses of the hold, right at the port and starboard corners.
This means no matter how the ship pitches or rolls in the waves, the water is going to find its way down to those extreme bottom edges.
Gravity and the geometry of the hull work together to funnel any rogue liquid directly into those wells.
Precisely. And because these cargo bilges normally contain only relatively clean water, the manual points out that this water is typically pumped straight overboard into the ocean.
Okay, I want to focus on the photo provided for this bilge system, because this is where the gritty reality of maritime engineering really hits you.
It's a great photo.
It is. We're looking at the lowest, darkest corner of a steel hold, and the metal is heavily pitted and covered in thick rust. And sitting flat on the floor in this corner is a heavy, square metal box covered in holes.
Right.
It's bolted to a thick pipe heading straight upward. Honestly, it looks exactly like a giant, rusty, cube-shaped cheese grater.
In the schematic, that cheese grater is formally identified as the strum box.
The strum box.
Yeah.
But wait, if this strum box is just sitting in a dark corner constantly exposed to salty bilge water, won't it just rust over and clog up entirely? How does a rusty perforated box actually protect the ship's high-tech pumping systems?
Well, the heavy iron construction and the inevitable rust are simply realities of the maritime environment. The strum box is an industrial primary filter.
Okay.
Think about what ends up on the floor of a cargo hold after a massive loading operation. You have loose grain, chunks of coal, shattered wooden pallets, plastic wrapping, and heavy flakes of rust from the hull itself.
Well, so it's a literal debris field.
Exactly. It allows the liquid to pass through its holes while keeping the ship-killing solids out.
Got it. So it's a heavy-duty strainer.
Yeah.
Okay, looking at the final mechanical schematic for the bilge system, we can trace the path of the water. We have the strum box sitting at the bottom of the well, submerged. Connected to it is a vertical pipe that travels upward and then takes a sharp 90-degree turn horizontally.
Yep.
This horizontal run is labeled the suction pipe, with an arrow pointing outward stating to E/room bilge pump.
The engine room bilge pump. It provides the immense vacuum power required to lift tons of water out of the hold. And the pump itself is kept safely in the engine room, completely separated from the cargo space.
But right below that 90-degree turn, sitting vertically on the pipe just above the strum box, is a component labeled the non-return valve. What is the purpose of placing a valve right there in the suction line?
If you consider the physics of pumping heavy fluids vertically over long distances, the non-return valve is arguably the most crucial single component in this entire bilge diagram.
Wait, really? Walk me through the physics of that. Why is it so critical?
Well, imagine the system in operation. The engine room bilge pump spins up and creates a massive vacuum. It pulls hundreds of gallons of water up through the strum box, up the vertical pipe, along the horizontal runs, and eventually pushes it overboard.
Okay, so you have a massive, heavy column of water moving upward through the ship.
Exactly. But what happens the exact second that pump shuts off?
Oh, the vacuum disappears and gravity instantly takes over. All that heavy water still sitting in that long run of piping is going to want to slam right back down the pipe into the cargo hold.
And the consequence of that is catastrophic. You have just spent energy removing dirty, salty bilge water to protect the cargo. If that water flows backward, you are actively flooding your own hold, dumping water directly onto millions of dollars of grain or sensitive electronics or whatever you are transporting.
Oh man, it defeats the entire purpose of the pump.
It does. So the non-return valve is the mechanical gatekeeper. It is a one-way check valve. The upward section of the pump forces the internal gate open, allowing water to flow up. But the absolute millisecond the pump stops and the weight of the water tries to fall backward, the valve slams shut against its seat.
Wow.
It physically locks the pipe. It ensures that the removal of water is strictly a one-way street, preventing a devastating backflow.
It's a backflow preventer. So simple, but absolutely brilliant engineering. If that single mechanical valve fails, you're literally turning your extraction system into a flooding system.
It perfectly highlights the overarching theme of these training materials. The ship relies on these foundational, almost brutalist mechanical systems to survive.
It really is beautiful when you step back and look at the whole picture. I mean, as a trainee today, you've essentially mapped the vital organs of this massive steel beast.
You've learned how it breathes and how it filters.
Exactly. You understand how a ship breathes passively, using thermal convection, pulling air down through its trunking, and how it actively forces air using mechanical blowers capped with aerodynamic mushroom caps.
And you know the terrifying importance of slamming a fire flap shut to choke a blaze.
Right. And you know how the ship stays dry using those rusty sacrificial strum boxes and the strictly one-way non-returned valves tucked away in the deep port and starboard corners?
It is the literal life support system for the global supply chain. These mechanisms of air and water flow are what prevent millions of dollars of goods from spoiling due to internal condensation or flooding from the bottom up.
It completely changes how you look at a cargo ship floating on the horizon. It's not a static, dead box. It's constantly regulating its own temperature, its own pressure, and its own fluids.
A highly active, highly engineered organism.
It is. But before we wrap up this deep dive, I want to leave you with one final thought to mull over. It's something that caught my eye in that very last bilge schematic.
Oh, I know what you're going to say.
It's crazy, right? We talked about the advanced physics of the pumps, the strum box, and the non-return valve. But running perfectly parallel to that suction pipe, dropping straight down from the main deck all the way to the darkest depths of the bilge well, is a completely separate hollow line labeled the hold sounding pipe.
A very easily overlooked detail in the diagrams.
It really is. It just sits there, a simple metal tube leading into pitch blackness. And the reality of what that pipe is used for is staggering. Think about the modern world. We have billions of dollars of high-tech, global trade electric cars, microchips, advanced pharmaceuticals, all loaded onto these hyper-engineered vessels.
Right.
Yet, to find out if the ship is secretly taking on water and sinking, the crew doesn't just rely on a digital sensor. They rely on that sounding pipe.
It is the ultimate low-tech failsafe.
They literally take a weighted string or a measuring tape with a brass weight on the end, drop it down that rusty tube into the dark, and listen for the splash.
Just listening for the water.
Yeah, they reel it back up to see where the water line is on the tape. The juxtaposition is wild. The fragility of our incredibly advanced modern supply chains ultimately relies on a sailor dropping a piece of metal down a hollow pipe just to check if the ship is drowning.
It really puts it all into perspective.
It really does. Something to think about next time you order a package from across the world. Thanks for taking the plunge with us today on The Deep Dive. We'll catch you next time.